Okay, so what we're looking at right here, this is the absolute workhorse of pretty much any process industry. A single-stage centrifugal pump. Its whole job, its entire reason for being, is to move fluid from point A to point B. And it does that by taking rotational energy from a motor and converting it into pressure. It's a simple, but man is it an elegant machine, and it's absolutely essential to countless operations out there.
So how does this thing actually do what it does? Well, let's just follow the liquid, right? It comes in over here on the left through the suction nozzle and gets sucked right into the very center, what we call the eye of that spinning impeller. Once it's in there, the vanes grab it and just fling it outwards at a really high speed into the pump's outer casing.
And this, right here, this is where the real magic happens. We're talking about energy conversion. So you've got the motor, right? It's providing the spin through the shaft. The impeller takes that rotation and translates it into pure velocity, kinetic energy, in the fluid. Then, the casing, which has this special snail shell shape called a volute, is designed to gradually get wider. That forces the fast-moving fluid to slow down, and that deceleration cleverly converts all that speed into potential energy, which we see as pressure at the discharge.
All right, so to really get how that energy swap works, we've got to look under the hood. Let's break this machine down and check out its most critical parts.
You know, it really boils down to three main players doing all the heavy lifting. First, you've got the impeller. That's the heart of the pump, the part that's actually spinning. Second is the stationary casing, or volute, that holds everything and manages that pressure conversion. And third, you have the shaft, which is basically the drive shaft, connecting the whole thing to the motor to deliver that power.
So let's see how they all play together. The impeller's job, get that fluid moving fast. The volute casing, its job is to slow things down, to build up that pressure. The shaft, well, that's easy. It's just delivering the raw power. But there's one more piece that's absolutely critical, the seals. You see them tucked away in what's called the stuffing box. Their whole purpose in life is to keep the process fluid inside the pump and not leaking all over the floor where the shaft has to pass through the casing.
Now, you know, out of all those parts, the impeller itself is probably the biggest decision an engineer has to make. The design you pick has a massive impact on what the pump can do and where it can be used. And it really comes down to one key choice. Are you going to go with an open or a closed impeller?
And this slide just lays it out perfectly. Look over on the left. That's a closed impeller. See how it has those walls or shrouds on both sides of the vanes? That makes it super efficient and lets it run with really tight clearances, so it's perfect for clean liquids. But now, look at the ones on the right. Those are open impellers. They don't have that front wall, which gives them way more room to pass stuff through. So if you've got solids in your fluid, this is the design you want to avoid clogging.
Okay, so with all that in mind, let's put this theory into practice. Let's look at a real-world engineering challenge. What happens when you need to generate really high pressure?
All right, here's the mission. We've got to get clean water into a boiler that's running at super high pressure. And here's the catch. The plant is packed. There's almost no floor space to put in new equipment. So, what do?
And here's our answer. This beautiful piece of engineering right here, a vertical multi-stage pump. Its design is just tailor-made for this exact problem. Let me show you why.
Okay, now this is the cool part. The reason they call it multi-stage is because, well, look inside. It's not just one impeller. It's got a whole stack of them, one on top of the other. The liquid comes out of one stage and goes straight into the suction of the next, and each time it gets another pressure boost. It's literally like having a whole series of pumps all crammed into one sleek package. So you can see how the logic just clicks into place, right? You need high pressure? No problem. The multi-stage design handles that by adding pressure bit by bit. You're tight on space? Easy. We'll just stand the pump up vertically. It barely takes up any floor space. And since we're pumping clean boiler water, we don't have to worry about solids, so those super tight internal clearances are actually a huge plus. They make the pump incredibly efficient.
All right, so that was the clean, high-pressure world. Now let's flip the script completely and dive into a totally different and, frankly, much messier challenge, pumping fluids that are full of solids.
So now the job is to move a chemical slurry. And we're not just talking about liquid anymore. This stuff is loaded with abrasive solids, and it's corrosive to boot. If you put that nice, efficient boiler feed pump we just saw in this service, man, it would be torn to shreds in no time at all. I'm talking hours, maybe even minutes.
Yeah, for this kind of nasty duty, you need a completely different beast. You need a heavy-duty slurry pump. This machine isn't designed for elegance or efficiency. It's designed for one thing and one thing only: survival.
Every design choice here is about being tough as nails. To fight off that abrasion and corrosion, the internal parts are way thicker,
And they often have these replaceable liners made of rubber or super hard metal. To deal with the solids, you guessed it, it uses an open impeller and has huge internal clearances so nothing gets clogged. The whole thing is just built like a tank for maximum reliability, no matter how bad the service gets.
And this is where we hit a really critical trade-off. The source material says it perfectly. These heavy-duty pumps are significantly more expensive to buy and operate. And that's the thing, right? These monsters are way more expensive. But that extra cost is what buys you the reliability you absolutely have to keep the plant online.
So really, it all boils down to this one fundamental engineering question that these two examples just highlight so well. When you're picking a piece of equipment, what's more important? The initial price tag or the long-term reliability and, the cost of what happens if it fails? As we've just seen, there's no single right answer. It all depends on the specific problem you're trying to solve.